Welcome to this OST2 lecture about TPM keys, key generation, key management, and hierarchies. Keys by the TPM is vital for its operations. Therefore, we'll take a bit of time to understand how it internally works. First and foremost, we need to know that private key material can never leave the TPM in plain form. The keys are either encrypted or not stored. Keys that are usually not stored are primary keys that can be regenerated every time. To regenerate these keys, of course, we need to have the proper authorization, and also we need to know what seed was used. There is an internal seed built in the TPM put there by the manufacturer, and also the TPM allows the user or the TPM owner to provide additional seed, additional entropy to the key derivation function, KDF for short. By using the same user entropy added to the internal seed, we can guarantee that we will generate the same primary key. The private material of private keys never leaves the TPM. We can only regenerate them. There are some optimizations we can do to avoid the regeneration, like persisting a TPM key, and this is covered in one of our other lectures. Child keys are typically the keys that are used to perform the various cryptographic operations like signing or encryption and so on, where primary keys are used to encrypt and protect the child keys. We also call this wrapping. The primary key is wrapping the child key. This is also one of the reasons why, in order to create a child key, we first need to have a primary key. To load the child key, we also need to have the authorization for the primary key in order to be able to decrypt, unwrap the child key inside the TPM, and then finish the process of loading so we can actually use it to perform some operations. A fundamental feature of the TPM is that it can have many key hierarchies. The TPM has fixed hierarchies that always exist, and key hierarchies can be created by the owner. They are defined by the primary key. Under the owner hierarchy, we can have as many as we want key hierarchies. This is also true for the other hierarchies, but it is unlikely that we'll do so. Because of the special purpose of the different hierarchies, usually the owner hierarchy is mostly used. For example, the platform hierarchy is where the OEM, the system builder or integrator, places different objects. The OEM initializes these objects or puts them there during manufacturing. The platform authorization is randomized at system boot usually, and this is done by the first OEM software. Would that be a UEFI? Would that be BIOS of some kind, or other firmware that starts first? The platform hierarchy starts with an empty authorization that is randomized on every start. That's what we need to remember here. On the other hand, the endorsement hierarchy is what's used by the TPM vendor to place some special objects. For example, the endorsement key. The endorsement key is a unique primary key that is created using the internal seed of the TPM and has properties defined by the trusted computing group. Of course, for your purposes, you can create different primary keys under the endorsement hierarchy. It's all depending on your requirements. The good thing about the endorsement key is that we can use it for machine identity in a standardized way. The owner hierarchy we already covered. You can have as many keys as you want, and the good thing is that each primary key has its own authorization. So the hierarchy authorization does not prevent you to have different key owners below, which is important, especially for large systems, automotive, and others. The last hierarchy is more special than the others in that its seed is never the same. The so-called no hierarchy is seeded at every power cycle of the TPM. This means actual power off and power on. If you just put your computer to sleep, there's no guarantee that the seed will change. But if you turn it off completely and then start it again, then the TPM guarantees that the moment it has voltage, it has power, it will be seeded differently. This is used to generate temporary keys that are used one time only. The benefit of having different hierarchies and different authorizations is that this gives us flexibility when we are managing the system. For example, we can have a device that is managed by organization control the endorsement hierarchy. On the other hand, the end user can control the owner hierarchy. This is very often the case in some managed scenarios. All of the hierarchies are available for taking ownership. Perhaps the platform hierarchy is the most difficult because if you have a very integrated system, the UEFI or the bootloader already randomized the platform hierarchy, and you might not know what that randomization is, what password is set, maybe even fixed. All the rest are usually empty authorizations that need to be provisioned, need to be set upon use. The endorsement hierarchy comes with a default policy, and this is important to note. This is defined by the TCG and is publicly available. We'll talk about more that later. Primary and child keys are the two types of keys, and we need to differentiate between the two. Primary keys can perform operations like signing, encryption, decryption, but usually they're used just as a step to define a key hierarchy, and they're used only to wrap the child key. Child keys are the ones that we usually associate with different operations. In each of these steps, when we generate a key, there's an internal seed being used, and there is a template that we can provide in the process, either through an API or through using the tools. This is much more than just the type of key. Is that an RSA key, ECC key, and so on? Such kind of properties go into the template that we pass to the KDF function. Including in that template is the unique field that allows us to add user entropy. It is not necessary to use that field. You just need to know what was the value of that field. If you're not using it, then it's zeros. That's all fine. It is important for the generation of the primary key or its regeneration. After that, we take seed from the primary key and a new template for the child key, again user provided, and we generate a new key. The second template again comes completely from us, so the unique field allows for user entropy, the key parameters, is it 128-bit or 192-bit AES static symmetric key, for example. This is all up to the user, to the TPM owner. We already mentioned some of the supported algorithms by the TPM. This varies between different models and vendors, but there is a minimum that the TPM must provide that is defined by the Trusted Computing Group. Here I have just given an outline of what typically is supported by a TPM. We have a lecture where we'll see how we can check the capabilities of the TPM. Of course, the easiest would be to consult the datasheet, but to be certain, it's best to use some of the internal commands the TPM provide to check what is actually supported. Aside the usual asymmetric and symmetric keys that we can find here, there is also this separate category of keyed hash keys that are used usually for HMAC operations. On the left side, you have the abbreviations as we're used to seeing them. On the right side, you have an example of how the TPM2 tools expect these abbreviations and parameters passed. Please notice that the key type and the key size are put together as one word. And of course, there is an alternative naming scheme where we have extended names using the NIST definitions. There are many internal types when generating a TPM key. It is easier to use TPM2 tools to generate the key that we need, and it will come with the right key properties. For example, if we need to generate a signature, we will have TPMA underscore object underscore sign as a property being set with that key. If the key will be used for decryption, then it will be underscore decrypt. Now, here comes the interesting part. Usually, primary keys do not support signing. And this is by design. It is possible, but by default, the primary key is meant only to wrap the child key. This is especially true when we have the endorsement key. The endorsement key does not have the capability to generate signatures. because it is missing the TPMA object sign property. The TPM simply cannot generate such key, and it is not mandated by the TCG that such key is a valid endorsement key. There are other interesting properties like fixed TPM and fixed parent that restrict a key and it cannot be transferred between different TPMs, which is in most cases the default. Once you generate a key, it is fixed to the TPM seed, and only this TPM can unwrap it, load it, then the primary key unwrap loads the child key, and so forth and so forth. If you're interested, check the TCG specification for the TPM library. I've given the exact table where this information is. To create a primary key, we have a TPM22 with a familiar name. Please note that it is a one-word, create primary. As mentioned earlier, in most situations, we will be using the owner hierarchy. As the system owners or as the TPM user, this is the place where we will create our TPM objects, key hierarchies, and so on. Of course, the tools allows us to choose a different hierarchy if we need. There are situations in which we would prefer to use the endorsement hierarchy. In some cases, attestation, a process to generate evidence about the system with the help of the TPM, are created under the endorsement hierarchy. When selecting a hierarchy, make sure to provide the proper authorization. Usually the authorization is empty, so when we start using the owner hierarchy, we can just keep that parameter. It is recommended to provide a password for your key so no one else can use it, including no one else could load it to the TPM. Without password, anyone could use the TPM key you just created. When selecting a key algorithm, remember that we need to also specify not just the type of key, RSA or ECC, but also some properties, either the size of the key or the curve. Of course, there are defaults that we can use, but it's always better to define in a more verbose way, so you know exactly the type of key you have and that it's compatible with the system and operations you need to perform later. The way TPM2 tools work is not just creating the key and having it in the TPM, but also providing us a way to save the context of the TPM at that moment. The context as the TPM is loaded with its properties. Using the -c argument, we can save that context, which makes it so much easier to use later for child key generation and other operations. This would be the recommended path forward. As mentioned earlier, the user of the TPM has the ability to provide additional entropy to the KDF process. This is done using the -u option, and it can be provided as a file or from the standard input. Here we have two simple examples of generating primary keys. The one generates an ECC P256 curve key, the other an RSA 2048-bit key. In the one case, we have not provided a hierarchy. We have not defined a specific hierarchy because the default is the owner's hierarchy. It is perhaps better to have that explicitly when running commands just to make sure you know where the key is created on. Notice that the parent object is provided with capital C, capital C, and the object being generated, or the context in this case, is with lowercase c. This kind of naming is preserved across the tools. You will see this type of naming across all TPM2 tools. Often, the key that we generate would have to interact with other systems, not just the TPM, and more likely it will be the public portion of the key. For that purpose, the TPM2 tools provide a very easy interface to output the TPM public key in a well-known format. By default, this is the TSS format that will just give us the binary blob with the private protected part and the public part according to the TPM specification. What we usually need is either a PEM or a DIR format for various tools, not just OpenSSL, but it comes in an OpenSSL compatible format. This is important to note if you're using a different cryptographic library. -O specifies the file name of the output. -F specifies only the format. Now that we have a primary key, we can generate a child key. For that purpose, we have another easily to guess TPM2 named TPM2create. This tool takes the parent context, which is no longer the hierarchy, but the primary context of the primary key. And it comes with a capital C. Then we have the child context, which will be the output, the result of our operation of the TPM key. This will store the whole key, the private and the public part, but the private part is already encrypted and protected before leaving the TPM. So even though this is stored outside the TPM, this is secure. Other than the context of the TPM, we can also store the separate parts of the key as private and public. In some situations, this is easier. In other situations, this will be needed. It really depends on the operations you plan to use from the TPM. For the purposes of our exercises, we'll use the TPM context option, so we'll be saving mostly the TPM context and not the separate private and public part. Here is an example of generating a child ECC256 key. We have done more than just specifying the type of key, but we have also specified the signing scheme we want to ECDCA. Also, when we created the key in the first example, we saved the key as private and public part, rather as a TPM context that we can later use. In the first example, we would need to execute TPM2load with the private and the public part to start using the key. It is important to know that the primary key type has no impact on the child key type. Remember that the primary keys can only be asymmetric, but the child keys can be asymmetric, symmetric, or keyed hash. This is the reason for that design choice. The primary key is used just to protect the child keys and provide seed. Therefore, you can even have an RSA primary key with an ECC child key. I would recommend sticking to the same type of key. If you have an ECC child key, keep to an ECC primary key. And also keep in mind RSA operations in general take more time. But this is up to you to decide based on your system and application requirements. While child keys can be stored in several forms, if you decide to use the TPM2 tools more, I think you would appreciate having the TPM context more than having the separate private and public part. At the same time, to integrate with different systems, make sure to use the formatting option to get a well-known format that can be integrated easily. If you generate the TPM key as separate parts, as mentioned, please make sure you use the TPM2load command. Otherwise, the TPM would not have your key ready for use. And in most TPM, there is a command that can do these operations together. For the purposes of this course, we will always do that separately or use the TPM context. This is the typical workflow for our labs, where we will generate a primary key, child key, and perform the operation necessary for achieving the goal of the exercise. Then we will flush the TPM objects because the TPM has limited storage. It has usually 3 to 7 key slots for keys in memory ready for use, and the same amount of number, 3 to 7, depending on the model, for persistent keys that are constantly available that we can swap out, place again. We'll talk about this in another lecture. Just remember that if you run out of key slots, you can always use the TPM2 flush context command. And depending on what you want to flush, if it's a newly created object, then it's probably a transient object. If it's a TPM session, we're not there yet, but there is the -L switch to flush loaded sessions and saved sessions. To seal data inside a newly generated key, we have to use the -I switch to the TPM2create command. Once we generate our child key, we can perform various TPM operations. The operation here is special with that it happens and takes place during key generation. The TPM can seal in two different ways. The one is inside a freshly generated TPM key. The other is against platform configuration registers called PCR, and we will learn more about PCRs in the advanced TPM course. Sealing a secret inside a key is limited by size because it takes part of the TPM key structure. The size is 128 bytes. This is plenty for sealing a secret, configuration string, or even a symmetric key. An example of how to seal some arbitrary data is provided on this slide. And please note that the sealing happens during key generation. What's missing in this example is the generation of the primary key that happened sometime before. When we have our object, our sealed object, we can unseal it using the TPM2 unseal command. If we have set a password phrase to protect our child key, then we would have to provide it to the TPM2 unseal. The output of the TPM2 unseal command is usually the command line, the terminal window that we have open. We can redirect that with the -O option. Creating digital signatures using the TPM requires the child key to already exist. In contrast with the previous operation where we sealed data inside the TPM key and we had to do it during generation, here we need to have the key generated and loaded into the TPM to be ready for use. We can generate digital signatures using the TPM2 sign tool. There is a mandatory option -O to store the signature, which is the result of the operation. The opposite procedure, verification, has the TPM2 verify signature tool. There we would have to provide the original message and the signature we generated with TPM2 sign. There's an example below.